Hi, my name's Daniel Glavin, and it's a pleasure to be here to talk to you today about the search for chiral asymmetry as a potential biosignature in samples from Mars. If you're interested in learning more about this topic, I encourage you to follow the link at the bottom of the page, which will take you to a review paper in Chemical Reviews, which describes this topic in much greater detail. So the motivation behind this work and the Chemical Reviews paper is that currently the search for chemical biosignatures in our solar system is focused on characteristic features of life as we know it. And one of those features is known as homochirality, and this is the predominance of left-handed amino acids and proteins and enzymes and right-handed sugars and nucleic acids in all life on Earth. This property of homochirality is thought to be a unique signature of life and, in fact, potentially even a prerequisite for life. However, we know from our analyses of some primitive meteorites that these materials can also have large left-handed amino acid excesses, up to 60% and even higher, that are made by non-biological processes. And this certainly complicates the use of using chirality as an unambiguous definitive biosignature. To address this, we propose a set of measurement criteria illustrated by the Venn diagram on the right to establish the origin of chiral amino acid asymmetry in future life detection experiments on Mars or elsewhere. We know from life on Earth that biochemistry is distinct from the abiotic chemistry that we see in meteorites and that we discover in laboratory simulation experiments. Life contains a very simple distribution of amino acids. Only 20 standard amino acids are encoded in terrestrial proteins. And as I mentioned before, they're all of the left-handed enantiomer. In contrast to biology, meteorites contain a much more complex distribution of amino acids. 96 amino acids have actually been named in the Murchison meteorite. This sample is actually believed to contain hundreds of different amino acids. Most are non-existent in biology, and they contain racemic mixtures, that is, equal mixtures of the left and right-handed forms. There are a few exceptions where some amino acids in these samples do contain large left-handed excesses, up to about 60%. However, it's worth noting that no significant right-handed excesses of amino acids have been found in any meteorite sample to date, and this points towards an early solar system bias towards left-handed amino acids, which I will talk about later. Another distinct feature of life is that there's isomeric preference. We see only alpha hydrogen amino acids in proteins. In contrast, in meteorites, there doesn't appear to be any significant isomeric preference. We see near complete structural diversity of amino acids in Murchison and other meteorites. For example, all possible isomers, alpha, beta, gamma, delta, etc., are found in these meteorite samples. And then finally, in life, we see isotopic depletion. This is due to a kinetic isotope effect and biological fractionation, where we have a stronger preference towards the lighter carbon, nitrogen, and hydrogen in organic matter. And in contrast to biology, we see many of the isotopes of organic material in meteorites that's enriched in the heavier isotopes, carbon-13, nitrogen-15, and deuterium, as illustrated by these more positive values. And this is attributed to their formation in cold environments. So on this slide, I show some hypothetical amino acid chiral distributions and possible origins. So starting from the left, you see the case where left-handed amino acids are much, much greater than right-handed forms. This could, again, be either due to biology or could be abiotic chemistry, as we see in meteorites. A more compelling biosignature would be cases where you have right-handed amino acids favored over left-handed amino acids. And this is because we don't see this in meteorites. We could rule out terrestrial contamination because those would attribute mostly left-handed amino acids. And this would be really exciting because it would indicate a unique, potentially, origin of life from Earth if we detected this on Mars or elsewhere. However, as I noted before, it appears that the early solar system may have been biased towards left-handed amino acids from the very beginning. So this situation may be less likely. So the question becomes, how can we make it easier to distinguish between abiotic and biotic origins of chiral asymmetry in more likely cases where you either have a racemic mixture or the left-handed enantiomer is favored over the right-handed enantiomer? One way to do that is through isotopic measurements. Here, illustrated by this slide, we see on the left y-axis the D to H ratio, illustrated by delta D notation, and then on the x-axis, the carbon-13 to carbon-12 ratio, illustrated by the delta 13 carbon ratio. And here you can clearly see that extraterrestrial amino acids, shown by the blue box, found in meteorites, can be separated from biotic amino acids by these isotopic compositions, which again are more enriched in the heavier isotope in extraterrestrial materials. The same analyses have been done on sugars, and again we can separate out biological sugars from extraterrestrial sugars by the carbon isotope ratio. So back to the Venn diagram here, where we propose the criteria to establish origin of chiral asymmetry, which includes, of course, detecting chiral asymmetry, looking at the distribution of amino acids as well as their isotopic compositions to help more firmly establish their origin. And where these all three overlap, you have a more compelling biotic signature. And I'll take you through some case examples here to illustrate this. Let's start with the Tagish Lake meteorite. This is a primitive carbonaceous chondrite, fell in northern British Columbia in Canada on January 18th, 2000. What made this fall so special is that it was an observed fall, and it also fell in a frozen lakes, which kept it preserved, so it was kept at very cold temperatures. We analyzed this material using a couple different techniques: liquid chromatography mass spectrometry, illustrated there by the bottom left chromatogram, and then gas chromatography mass spectrometry to measure the isotopic ratio of amino acids in this meteorite. And what we found is that we do have chiral asymmetry for a few amino acids. Aspartic acid is shown there in the bottom in the GCMS plot, where we see an L excess of aspartic acids of about 60%. Although it's interesting to note that not all protein amino acids in this sample had L excesses. Others, for example, alanine, were racemic. So again, this suggests that there was not significant biological contamination of this meteorite. Nevertheless, we do satisfy the requirement for chiral asymmetry. Where we fail is in the distribution. So here we see a very complex distribution of the amino acids in Tagish Lake, like we found in the Murchison meteorite, with near complete structural diversity of 2 to 8 carbon amino acids, including all possible 5 carbon amino acids illustrated by the red box, where we see alpha, beta, gamma, and delta isomers. So again, this is not a signature of biology. This is a clear signature of abiotic chemistry. And then finally, we also don't see the light isotopic composition. So the amino acids in Tagish Lake are heavily enriched in carbon-13, clearly falling outside of the terrestrial carbon isotope range for aspartic acid. So again, although we see the chiral asymmetry in this meteorite, this is a clear indication of abiotic chemistry. Let's take the other example of a clear biotic example. So this is terrestrial soil collected from Costa Rica near the Aguas Zarcas meteorite fall. Again, analyzed it using the same techniques, LCMS and GCMS, to look for amino acids in the sample. Here, again, we satisfy the chiral asymmetry requirement. In this case, we see L excesses for all chiral amino acids. So it's not just glutamic. We see the L excesses for all protein amino acids. And this is different from meteorites, where we only see these excesses for a few amino acids. Here, in contrast to meteorites, we see a very simple distribution of 2 to 6 carbon amino acids with only one 5 carbon amino acid isomer here, and this is valine. This sample is dominated by alpha hydrogen amino acids, so again, we do see the simple distribution and structural isomeric preference that we don't typically see in meteorites. And then finally, the carbon isotope measurements, not surprisingly, are carbon-13 depleted. We see this in DNL glutamic acid. We also see this depletion in other protein amino acids analyzed in the soil, which all fall within the biological range. So here we have a clear biotic signature. which is not a big surprise. Now let's go to an example that's more relevant for Mars. This is a very interesting Martian meteorite called Roberts Massive, RBT for short, 04262. It's a Martian shergotite. It was ejected from Mars about 3 million years ago and found in Antarctica by ANSMET in 2004. Again, we make similar measurements on this meteorite as we've made in other meteorites using LCMS and GCMS. And what we found was very interesting. So here we actually do see a simple distribution of amino acids satisfying that requirement. We see a strong preference for straight chain N-omega amino acids, glycine, beta-alanine, and gamma-amino N-butyric acid. So a very simple distribution. So we do satisfy that requirement. Interestingly enough, we also see depletion in carbon-13 isotopes. And this is a measurement that was made for beta-alanine, delta-13C value of -24 per mil, which is similar to the carbon isotopic composition of reduced igneous carbon found in other Martian meteorites, as well as thermally altered carbonaceous chondrites, is also consistent with Fischer-Tropsch type reactions and overlaps with terrestrial biology. So we do satisfy that requirement, starting to get pretty interesting. However, it should be noted that these straight chain N-omega amino acids are not chiral, so there is no chiral asymmetry. So we do fail that requirement for life. So again, interesting distribution here, but not biotic. So one of the challenges with searching for amino acids on Mars in particular is that Mars does not have a magnetic field, so it's not protected from the cosmic radiation and solar cosmic radiation like we are here on Earth. And this radiation can penetrate very deep into the surface, 1 or 2 meters, and will destroy organic molecules over time, including amino acids. So this is going to be one of the big challenges for Mars exploration, especially the analysis of samples collected from the near surface, where we might expect very trace levels of amino acids and other organics. One strategy to get around this is from the ExoMars rover, which will carry with it a 2-meter drill. So can actually drill down below this ionizing radiation zone and hopefully acquire more pristine samples that have not been exposed to the radiation. This mission is scheduled to launch in 2022, and if successful, we'll make the first amino acid chirality measurements on Mars, which is really exciting. To do that, it uses an instrument called the Mars Organic Molecule Analyzer, or MoMA, which carries with it a gas chromatograph mass spectrometer, and also these tiny capsules filled with fluid. And in some of these capsules, you have DMF DMA, which can react with amino acids, any amino acids in the sample, at relatively low temperature, and form derivatives that are volatile and can be detected by gas chromatography mass spectrometry. And their enantiomers, the left and right-handed forms, can be separated and measured. So this is really exciting. Looking forward to doing this measurement hopefully in 2022, 2023. I will note that even MoMA does not have the capability to measure isotopes. So this is going to be a challenge, obviously, for trying to figure out the source of any chiral asymmetry. Mars sample return, hopefully right around the corner here. Of course, everybody knows the Perseverance rover launched in July of 2020 and is scheduled to land here in just over a couple weeks on Mars, and will collect samples as the first step of a joint NASA-ESA Mars sample return campaign. I think the up to 30 sample cores can be fetched and returned to Earth, hopefully in the early 2030s. Ultimately, coordinated analyses using state-of-the-art Earth-based laboratory instruments of a carefully selected sample set will be our best chance to detect and determine the origin of any potential biosignatures, looking at different molecular structures, isotopic patterns, and of course looking for trace amino acids and measuring their chirality. So in summary, the detection of chiral asymmetry will need to be carefully interpreted in the context of other key observations. One compelling biosignature would be the detection of molecules with the opposite handedness as life on Earth, but that may be unlikely. Enantiomeric excesses detected in chiral molecules that display isomeric preference and light isotopic compositions would provide a strong, compelling biosignature. Finally, I'd like to thank my co-authors, as well as the NASA Astrobiology Institute, the Planetary Science Division, and the Simons Foundation for funding support. Thank you for your attention.